right, everyone. Let's get started. Good morning, good afternoon, good evening for some of you, and welcome to today's webinar, A Protocol Guide to Micromilling for Microfluidics, here at our webinar series at BioProtocol, an open access online journal established here on Stanford campus 15 years ago, with a mission to make research more transparent and reproducible. Just a few comments to get the most out of this. If you have questions, you can post them in the Q&A or in the chat section throughout the talk, and they will be addressed at the end. And this webinar is also being recorded and posted later, so you can revisit it. It is now my pleasure to introduce today's moderator, Dr. Vishwa Vasani, who is currently a postdoctoral scientist at the EPFL in Switzerland. Dr. Vasani received her PhD in bioengineering from the Georgia Institute of Technology in Atlanta, working in the lab of Dr. Takayama, before starting her postdoctoral research work in the McKinney lab at EPFL in Lausanne. Her research interest focuses on tissue engineering and microphysiological systems, including organoid and lab-on-a-chip platforms to model complex biological processes in vitro. Trained as a mechanical engineer at the Indian Institute of Technology in Bombay, she brings an interdisciplinary perspective to biomedical research with the expertise in being in mechanistic modeling and microfluidics. And with that, Vishwa, I would like to hand it over to you.
Thank you so much. I would like to in turn introduce Dr. Hannah Viola. It is my great honor and pleasure to introduce Dr. Viola, who in my experience is a fantastic mentor, researcher, and communicator. Dr. Viola is currently a postdoctoral research fellow in the lab of Dr. Lonnie Shea at the University of Michigan, where she studies tissue engineering, tissue injury and repair using biomaterial-based strategies to modulate inflammation and fibrosis. Prior to her time at UMich, Dr. Viola earned her BS in chemical engineering from the University of Texas at Austin and her MS and PhD in bioengineering from the Georgia Institute of Technology. Dr. Viola conducted her doctoral research in the lab of Professor Shuichi Takayama, where she developed advanced in vitro systems to model lower respiratory physiology and inflammation, including a microfluidic airway-on-a-chip model to study respiratory crackle-induced stresses, and a high-throughput platform for human neutrophil transmigration. Her publications reflect a commitment to developing physiologically relevant systems that advance basic research and therapeutic discovery. And her excellence in this area has been rewarded by the Best Doctoral Thesis Award by the GT Bioengineering Program. With that, I invite Dr. Viola to share her insights from our recent publication.
Thank you, Vishwa. I am really happy to give this talk today, and I hope that it's useful to everyone. And we're going to be talking, like we mentioned, about microfluidics for biological applications. But first, I want to make some definitions so that everybody is on the same page. Is everything looking good with the slides? Okay, just making sure. So, everything looks okay? Okay. Just want to make sure everyone is able to see things. So microfluidics are generally devices that will manipulate fluids at the microscale, so the scale of like microns to nanometers. Biomicrofluidics is the application of these devices to manipulate or to model biological systems. And that can include applications like single-cell sequencing, where we partition single cells with a bead, and that has made huge advances biologically for mechanistic studies. And it also includes the organ-on-a-chip systems that we've probably all heard about, where we take human cells and we can co-culture them, control the conditions by controlling flow at this microscale. The technique I'm talking about today can be applied to both of these applications, but my particular study was on organ-on-a-chip, so the device that I'll be talking about today is focused more on the organ-on-a-chip side. So I also want to talk about the fabrication methods that we're used to seeing and why micromilling is a little bit different. So to talk about that, we have to talk about like the casting process. So typically we'll make some kind of mold, which will be a positive impression, and then we will cast the polymer on top of that mold. Usually we use what's called PDMS, polydimethylsiloxane. I'm going to get my laser. So we'll usually make this kind of master mold, we call it, and then pour some kind of polymer on top of it. We usually use the PDMS, and then we have our device, which will be a negative cast. And the reason we usually do it this way is because you make one mold and then you can make lots and lots of devices using that same mold. So it's much faster and it's more reproducible. So what I'm really talking about today, I guess I gotta use a different button. There we go. What I'm going to focus on is how are we making this mold that we cast our PDMS onto. You can also directly mill or fabricate the device itself, but we like using PDMS because it's transparent. We can essentially like glue it to stuff. It has a lot of nice properties. It's biocompatible. So we're normally, when we're talking about the fabrication, we're talking about a mold that we're going to use to make devices. So the rest of my talk is going to be how do we make this mold. So first I'll introduce the method we're focusing on today, micromilling, which is CNC milling at the submicron scale. So let's define those words. CNC means that we're controlling a machine using computer code. So CNC is computer numerical control. And that's a common way we will program a machine to do precise movements. And then milling refers to the removal of material using a rotary cutting tool. So a tool like we have in the picture that is spinning and it's sharp on the end. So it's basically a drill bit that's spinning and it's going to remove material and create these chips. And this is a really common fabrication method in industrial places. So like pipe fittings, I used to be a chemical engineer and we would make pipe fittings using this technique. So it's well established in places like mechanical and industrial engineering, but we don't use it a lot in the bio space. But I think it's really useful. We're going to talk about why. But before I get to that, we have to compare it to the existing methods and say, why do we want to use milling instead of these other methods? Or like rather, what are the advantages and disadvantages of milling over other methods? So our most common method for making this mask that we'll cast our device with is going to be photolithography, where we shine some kind of UV light over another mask and then imprint the light, and that will create your pattern. And then you have to develop it, degrade all the other polymer, and that's how you get your mold. So this method is very high resolution. You can get down below the nanometer scale depending what technique you're using. It's very well studied. But the photomask, you might notice, that also has to be created somehow. So we have to use laser etching to make the photomask. That has to be done in a clean room. It can be difficult. You might have to outsource that part of it. It does have a pretty low aspect ratio. So the height to width ratio, you cannot make very tall things. And you can only make two-dimensional features because the method doesn't allow you to make a curved thing. So that's something that curves in the z-axis. You can't really do that with the photomask. And finally, the master molds are made of polymer. They're relatively fragile, and you have to get a spin coater involved. So you need a lot of equipment for this technique. So if you're set up for it, it can be pretty good depending on your application if you want something with a small resolution and you don't care about those 3D features. So another common method is 3D printing. So this is extrusion 3D printing, where we have some kind of polymer and we're pushing and we're heating it a bit and then kind of extruding it and building layer by layer to create our part. So this is relatively easy to use machinery. A lot of places have them. They're pretty fast in terms of your fabrication time compared to other methods. You can set it up and get your part within a day or two, which is pretty fast. You can do 3D features, so you can have rounded features, and the aspect ratio here can get really, really high, which may not necessarily be beneficial depending on most microfluidics. You don't need that kind of aspect ratio. But the other consideration is you can make stuff that's kind of big. Depending on what your device is, some devices can be pretty large overall. And if you need that kind of footprint, 3D printing is able to do that, sometimes at the cost of the resolution, but it depends again on your application. The downsides are that the resolution of 10 to 20 microns can cause what we call a staircase effect. As we go up in layers, because the resolution is like this, you can kind of get this effect depending on how small your features are, and that can be undesirable. So one of the reasons I didn't use 3D printing for the model that I developed was this staircase effect. We noticed that was kind of a problem for our design. Also, thermoplastics that are used for extrusion printing do lower their viscosity with heat. So although their melting point is more like 400 C, it's not impossible to get some kind of warping at the temperatures needed to bake PDMS that you might want to cast on a 3D printed part. So that could become an issue as well. And then the most, I would say, technologically advanced 3D printing method is called 2-photon polymerization. You take two lasers, and where those lasers intersect, you polymerize the material, and you can get very, very high resolution with this, back to under 100 nanometers, and you get the high aspect ratio. You can also do very complicated designs, overlapping things and interweaving features. But this is less accessible, I would say, than other methods. The object size is pretty small still. Maybe it's improving now, but you can't get too big with this, bigger than a couple centimeters in every direction at best, I would say. And it's relatively slow and expensive for a lot of microfluidic applications. I would say personally, it's like more advanced than what we need. And I haven't personally done this method, but I doubt that it's faster than micromilling or more accessible. Because I've never even met anyone who's done this before. I'm sure people are doing it. But the reason that I like micromilling is that it gives us resolution in the range that we need it to be. So around 1, you can make a feature of 1 micron plus or minus 0.1 with the right tools, which is kind of right where we need to be for microfluidics. A lot of them are in the like micron range, half a micron range. Mine, I think, was 25 microns. I don't remember off the top of my head. It's in the paper. You can get a pretty good aspect ratio, about 5:1 with the right tools. You can do curved features. The mill is able to do a nice perfect curve in all 3 directions. We're not doing one layer at a time, so we don't have the staircase effect. It's pretty low cost per part. It's basically the cost of the drill bit you need and the cost of the material itself if you already have the equipment. So you can really churn out parts without spending a ton of money. And the equipment itself is relatively affordable as far as like fancy equipment goes, 20 to 30K. It depends on your perspective, but compared to some other instruments, it's relatively affordable, even for a single lab if you're well funded, or for a core center at a university, and it has a relatively small benchtop footprint. So it's pretty in the range we want, and you can do some pretty big stuff with it. The working area is relatively large compared to other methods. So if you needed for some reason to make a ridiculously big piece, you can do that. But you can't get too tall. 5:1 isn't a crazy aspect ratio, but you really don't need more than that for most microfluidics anyway. One of the major downsides of this technique is there's not a lot of people that know how to do it in academia. Like I said, it's common in industry that people use this technique, maybe not at the micro scale, but a lot of people will do it at the macro scale for making a lot of different types of parts. Pretty much any machined part is done with a method similar to this. And it does have a little bit of a higher surface roughness than like something like photolithography. I don't know about 2-photon polymerization, but this can also be mitigated with the right surface finishing protocol, the right tools, and it's often good enough for what we're trying to do. I've had really good success with like getting 2 layers to adhere to each other with micromilling. I know other people have used it for that too. So it's not perfect, but I think that it has a high enough throughput and the right resolution range that's why people refer to it as kind of a high throughput prototyping technique, that you can come up with a design, make it the same day. Maybe you have it by tomorrow. A lot of my stuff would take like 16 hours. So you'd run it overnight and then you have the device the next day. It's in your own lab, so you don't have to go out to a core or have someone at another lab fabricate it for you. So if you're doing a lot of microfluidics and you want to test out a lot of different designs, I think it's a great tool to have. Our lab has certainly, the Takayama lab has certainly benefited greatly from having access to this. And the last thing is it's very loud. So you've got to have a big case to put around it, or you have to have somewhere to put it because it can be kind of disruptive. But like I said, we run it a lot overnight, so it's not as big of a deal. This is just a summary slide. I've already talked about most of these things, but I'm leaving it in here in case anyone wants to pause later and look at the details. But I'm going to move on to the protocol so that we can spend more time on that. So this is a lot of steps. I'm going to go through them one at a time on this slide. So first we have to design the device. And you have to design your master mold. That's going to be in a 3D modeling software like SolidWorks. There's other ones, but the one I've used is SolidWorks. You also need to tell the machine what to do. So that's called a G code. This is a little outdated. They call this Fusion now, not Fusion 360. But you have to tell the machine exactly what to do. And that is done in a simulation that you will make in a program like Fusion. Then you have to actually make the mold. Then you're going to cast your PDMS onto the mold, assemble those layers. And then for my case, I had to functionalize the membrane because I made a sandwich device where you have a membrane separating two channels. And the membrane I used was not able to chemically bond with PDMS. So I have a functionalization step. But I found that is pretty useful if you're doing any kind of sandwich device. That's why I put it in the protocol. So the way that I fabricated my device is with plasma oxidation to chemically functionalize the surfaces so that they could covalently bond. And there's other methods for that, but I found this one is really good for preventing leaking. Then you have to sterilize the device and treat it with collagen so we can get the cells in there. And then you're going to do the culture. That's going to look different for whatever you're doing. I made a lung device, so I put in lung epithelial cells. So I'm going to talk a little bit about how do we design one of these devices. I think that SolidWorks has fantastic documentation for the basics of how to use SolidWorks, but that's why I recommend this program because it's very commonly used in the engineering field. I'm sure Vishwa took like classes about it in mechanical engineering. They work a lot with SolidWorks. And it has a lot of great documentation and tutorials. What I want to emphasize in this photo is how many reference planes are in this design. Every blue line is what's called a reference geometry, which is not, it's a virtual plane that you define in your design that you can attach features to so that you can exactly control the shape of your design. It makes sense when you get in there and start trying to do things, but it's when you're trying to fabricate a part in SolidWorks, and let's say you only wanted to change this part and not the rest of it, you have to put in these reference planes so that you can say, I just want to move this plane up 2 inches, and then it moves the drawing for you and it does everything for you. And it also ensures that all of your circles are the same diameter, for example. So if you put reference planes in here, I have a circle that has, this reference plane is actually referring to the bottom part. So the angle of the bottom channel is going off of this reference plane, which is 45 degrees exactly because it's in between these two reference planes. So just sticking to, and SolidWorks will have more detailed videos, but I want to emphasize how important this step is for your part, that you make sure all of your geometries are well defined and that your drawing, all of the lines need to be black. If any of your drawing lines are blue, that means that they're not fully defined. And if you change something else, that means that the drawing will get messed up in other places. And this is just something you have to practice. But I highly recommend the skill if you're doing fabrication because it's so powerful to be able to design your own stuff. And again, it goes well with micromilling because you can make something in SolidWorks and have it made in real life within a day. And that's really cool and gives you a lot of power to make and optimize different designs. There's also stuff on YouTube. I know that's not, I can't go into the details of like how to use SolidWorks in the talk, but there's a lot of great resources out there. And then once you have your top and bottom channels fabricated, I like to make those parts and then put them together. You can make what's called an assembly file in SolidWorks and overlay them to see what your final device will look like and make sure that the channels line up the way that they need to. And then I also make my master mold, which is just 6 copies, or 3 copies, I guess, of the device that are glued together, because this is what I'm going to mill. And this is another advantage of micro milling, that I don't have to make, hold on, I want my laser. I don't have to make one device at a time. And I guess this is true of like photolithography to some degree, depending how big your wafer is. I can make 3 devices with 1 cast. So I can fabricate this, and then maybe I make 2 or 3 of these molds because they're relatively cheap to make and easy to make. I could make 12 devices in one day if I really wanted to. And depending what you're doing, that can be really helpful, because if you've ever made microfluidics, you know how much time it can take just to make them. So having higher throughput on the fabrication side is nice. And then we need to discuss how we're actually going to design and mill the part. There's 2 ways that you can do it. I know I've done it one way, and then Vishwa has done it the other way, and it depends on your personal preference and what works for your design. The most common way is going to be that you just mill your positive mold with your design, and then you cast the PDMS, which is illustrated in blue here. And the advantage of this is you don't have an intermediate mold where you have to cast again. I'll talk about that in a second. And you can have sharp outside corners, which I have here. So the mill is going to have some diameter. You can get it a perfectly 90-degree corner on these outside corners, but then the inside corners are going to be more rounded depending on the diameter of your mill. And this might not be important. It depends on the ratio of your features to the size of your mill. But it can be a limitation to be aware of. The downside that I've found with this technique is that your adhesion surface gets milled, and sometimes that can increase the surface roughness compared to like the naive surface. And if you're using different tips, different like tools, and one of them is much bigger than another, or they're different shapes, they can sometimes have slightly different finish heights. They're supposed to be the same. I have found there's a very, very slight mismatch some of the time. Vishwa hasn't had this problem. I don't know if I did something wrong, or I don't know. I think some of the tools just have slightly different finish heights, and that can become noticeable depending what you're doing. And also depending on what you're doing, if you're milling outside of your features, that might take much longer than just milling the features themselves, depending on the surface area of features versus the surface area outside the features. So that was a problem for me that made it take longer than I wanted. And I also had issues with adhesion because this milled surface wasn't sticking good enough for me. And when I put it in cell culture, it would start to leak. So the other method that I personally decided to go with was milling the negative mold, which is milling the actual device and then casting an intermediate mold for the positive, and then going to cast your final device on this intermediate mold. So this gave me a couple advantages. I did not mill the naive plastic surface, which is pretty smooth by itself. So that left my adhesion surface perfectly smooth. I had a matched finish height because I was not finishing, outside my features. So, there was no finish height discrepancy to worry about. It took me less cutting time because I didn't have to mill all the stuff outside of my features. I just milled the features. And the downsides are that you have to make the intermediate mold, which I found is not that big of a deal for me. And then your inside corners are blunted, but depending what you're doing, this might not be a problem for you. I didn't find it to be an issue for me. So I prefer this method. And then the other advantage is I could make lots of this intermediate mold. I could make lots of these out of one milled part. So I could take the one milled part and make like 5 intermediate molds and then make a million devices out of that one fabricated part, which gave me a lot more throughput that, when you're trying to do an experiment with these things, you need to make like 100 of them. So I really appreciated that. So the next step is that you're going to tell the machine how to cut out your part. And this is a little bit difficult to approach from a beginner standpoint. This is the figure from the protocol. What it's going to look like, it's a simulation that draws out where that cutting tool is going and exactly what it's doing. throughout the cutting of the part, and you can even zoom all the way in. Here's the tool, and you can see exactly how it's going to move and even get an idea of what the surface finish will look like. It's not perfect, but it is pretty good. It's also relatively good at estimating how long the whole process will take, which gives you the opportunity before you go cut it out to see, is it going to be 2 days or 3 hours? And gives you an opportunity to see where are the longest steps and where can I maybe improve or get a different tool that might be better for that step. And that's kind of what the cutting process looks like. The tool is going to go, it'll go layer by layer this way if it doesn't have any rounded features, but it also has the capacity, like I show in J, to go up and down in kind of a rounded shape so that you don't have a staircase effect, which was really nice for my application. So I'm going to talk a little bit about, how we make these simulations. Again, the official documentation from Autodesk is great. They have really detailed stuff. This is a technique that's used a lot in industry. So there's a lot out there, and most of it will be the same for like macro scale machining versus micro machining. But there are a few discrepancies that I will focus on that are also discussed in the protocol. So one of them is that our end mills are actually so small that we have a taper zone. This, I found a real picture of an end mill. They tend to look something like this. You have the shank is going to be, about the width of a pencil or a little bit skinnier than that. Then you have a taper zone where it gets real small. And then at the very end, you have the actual cutting area. In this mill, it's just this 0.794. And the rest of it is just getting down to that size. And then when you zoom in, you can see there's 2 flutes. The flutes are these kind of wraparound cutting edges. Those are what actually remove the material. And these are important features because to make our cutting simulation, we have to tell the machine exactly what this tool looks like so that it can properly simulate the tool path. We need to know how fat the top of the tool is, how long it is till the actual part we work with so that we can avoid collisions and make sure that we are not drilling too deep and then colliding the part with this part, this taper part. And so that's why the fusion simulation is going to ask for the reach from the tip, which I usually give, the bottom of the taper zone, because I don't even want to go past up to the taper zone. I will just say, like, start warning me if I try to drill anything lower than like the skinny part of the tip, which would be probably here, I would say. And then the length of cut is the part that actually has the flute on it. And here that would be the 0.794. And then the tool diameter is this 0.397 in this tool. That's going to be easy to find because every tool that you buy provides these parameters because we need them to program the machine. And then in terms of your other parameters, we have to decide what we're going to cut. I like to use acrylic. You can use metal, wood, anything solid that doesn't melt easily is probably fine. Even metal, depending on the tip you're using. But I prefer acrylic for this stuff because it's easier to cut through. It doesn't take as long as something like metal because metal is tougher. So maybe you need to spin faster and go for a longer time. And it's just as robust for what we're doing. But people will carve out metal for things like making articulate jewelry, making art and stuff. You can do really any substrate that you want to try out. If you're willing to break a tool, then you can probably see if it works. The end mill diameter and shape is a big decision that you need to make, and that depends on what you're making. But I would use, for like a 100 micron diameter, I would try a 50 micron tool. You want the tool to be able to move around if you're doing something curved, you need it to be able to move. But again, like the simulation will also help you figure out if that's the right diameter for you. If it looks bad, the simulation will be able to indicate that. And then you can try out different diameters. Even if you don't even own the tool yet, you can go to websites. They have lists of all the tools that you could buy, and you can try out different ones in your simulation and see what looks good. And then you have to decide the shape. Micro tools usually only have either a round, what we call a ball end mill, or a square end mill. The ball is going to be a round at the bottom, which is like this tool in the picture kind of has a rounded bottom. And then the one that I drew was a square or flat bottom tool. So that's going to have a flat finish. The The ball end mill I like to use for clearing material and for creating rounded features. And the square end mill, I like to use it for surface finishing and for flat features, or if I have a part that doesn't have any 3D features, just to cut down. It's not super important. Again, the simulation will help you be able to tell if you're using the right shape and size, because you get really good resolution on what the final surface finish looks like. And because micromilling is not that difficult to do over and over, it's not that expensive, and it's not that time consuming. You can even just make the part and see if you like it and check it out. And if it's not working, try something else. So there is a bit of trial and error, but I'm assuming, most of us are experimentalists here. We're used to some of that optimization process. And then the other parameter that's really important is your spindle, which is the drill bit, the spinning part. How fast are we spinning, and how fast are we moving the spinning tool along the material? And those are called the spin speed and the feed rate, or colloquially feed-in speed in the manufacturing space. And that depends on a quantity we call chip load. So that is like how hard we're making the tool work. I'm going to talk a little bit faster because I want to get through the content, but I want to be done by 11:45 so we can get to questions. But feel free to pause me if you're watching the recording after the fact. So the chip load is how hard are we making this tool work? We want that to be around 4 to 6%. And that depends on both your feed rate and spindle speed. And then your number of cutting edges, that's the number of flutes that you have. I provided a spreadsheet in the protocol where you can see different example parameters. It depends on your machine. Some machines don't go up to 60,000 RPM, so you might go lower. It depends on what kind of chip load you have. Your chip load needs to be lower the more stiff your material is. If you're working with a metal, you might want to go down to 2%. But it's all, again, very kind of flexible and depends on your application and your design and what you like. At the end of the day, it's like, does the part look good or not? And that's kind of subjective. And it also depends, like a higher chip load will fabricate your tool faster. It'll fabricate your part faster, but it might also compromise the surface roughness, because the harder you're making the tool work, it might do a little bit of a worse job and get more surface roughness. So there's just all kinds of trade-offs. That's why it's a very experimental thing. In my protocol, I provided the parameters that I used for my part as a starting point. But, like I'm always saying, it's just an optimization thing you got to try out for yourself. But just to give you an idea of like how much information is needed to make the simulation and like how many decisions you have to make. It's a lot of decisions. And I mentioned in the protocol, I don't know why, but when I use Fusion, the coolant, if I put coolant in, it like breaks. So I just disable it. Even though I have a coolant in my system, I just don't include that. So the machine itself, we've got the spindle, that's the motor that spins the tip. We have a microscope camera to be able to see the tool tip a little bit better for the part where we're like leveling it to the surface. We have motors, you can't see them super well, but it's good to know where those things are. Most machines look pretty similar. So those are important things. And then we have to orient the simulation to the machine. So you have a simulation where you have some origin when you made this in Fusion, and you have to tell the machine where on your physical cutting surface that simulated origin should go. In order to do that, you can just set the X. It's easy to just place the tool above the spot where you need to start. I usually define that as the lower left XY coordinate of my part at the top of the Z plane. So that's what I need to tell the machine. I can put it in the XY part pretty easy by just manually moving it. But to get that Z plane, I have to slowly lower the tip until it's just touching the surface. And then I'm going to call that 0. But that has to be done manually. So there's more complicated or more detailed information about that in the written protocol, but we basically are just going to slowly lower that tip until we get to that surface. And then the machine knows this is the origin of your simulation, and then it's going to cut the simulation like that. And this is confusing. You have what's called the fixture offset. So once you tell the machine, this is the origin from my simulation, the machine has a different coordinate system that it's working with, so it has a different origin. It has an objective origin that is actually measured by the machine. So the machine is going to move the spindle to the maximum X, Y, and Z position, and it's going to call that the home origin for the machine. And that's based on physical probes that are located at every motor. So the machine is physically sensing and defining its own origin point. So you have to define your origin, the machine is going to define its origin, and then the machine is going to calculate the difference between those two. And the Z-axis difference is called the fixture offset. So the tip of your tool from this surface to the probe, actually, not the home origins. There's a third location we have to refer to. The difference between the surface of your working material and then your Z-axis probe is called a fixture offset. I did not bring in the probe, so let's talk about the probe. The probe is how we're going to empirically determine how tall the tool is, because we know where the spindle is, so the home origin is defined based on the spindle which holds the tool. But that's not actually where the tip of the tool is. So we have to define how long our tool is in addition to where the spindle is. So we've got now we have three origins. We have the work surface, we have the home origin, and then we have the tool probe, which is a third location. And we have to take the difference between the spindle height and the probe height, and that tells us how tall the tool is. And then we can add to the spindle height this tool length to get the exact location of the tool tip, because the machine needs that in order to properly cut your part. So the probing step is basically how long's our tool. Homing step is where is the spindle, and then we can add the fixture offset to the home origin Z-axis. I know it's confusing. I'm sorry. I hope it's better written in the protocol, but it's very confusing, and I don't want to spend too much time on it so we cover everything. But that's why we do our homing step, where we tell the machine where is the spindle, and then we do the probe step, where we tell the machine how tall the spindle is, and the combination of those two allows the machine to completely define the tooltip's location. And then we told it this is where the origin is for the cutting, and then we have all the information that we need to actually cut the part. So we are going to run our G-code out of the Fusion simulation, and hopefully that goes well and it goes perfectly and you don't break any tools, and it's awesome. And then we actually have to make the device. I'm going to go quicker through this part, but it's in the written protocol, and I hope you also find that helpful. So the way that I made my part is I casted a PDMS mold onto my negative milled part with 1:5 ratio of crosslinker to PDMS, and that gives you a higher cross-linking density, so that when you cast 1:10 PDMS onto the 1:5 PDMS, they actually do not bond to each other. I found this in the literature somewhere. Several people have done it, and it's really impressive that it works. It does work. I can confirm it. You know, you would think that they would bond to each other, but they actually don't. I surface functionalize my membrane and both sides, and then glue them together. You want to cook it a little bit to make sure those covalent bonds set. Incubate with some collagen, put your cells in, and then do your culture and whatever application is downstream. This is a pretty standard microfluidic fabrication protocol, but part of the reason that I published it was because there's so many out there, and none of the details are all included in the same protocol. It's kind of like some protocols in the methods, they'll mention one step or another, but this is like the whole thing. And I can tell you personally, it worked for me to do it exactly like this. So that's what these steps are going to look like. We have our master mold. It's really hard to see. I didn't take a picture when I was still working in the lab, but I wish I had the picture. But this is the micro milled mold that I have kind of put a barrier with tape around it so that I could fill the mold with the PDMS. And this is my like casted PDMS mold that I put in like a tip box lid because it fit perfectly in there. And then this is the bottom part and the two parts put together. You can store the PDMS cast of your part on some masking tape for like a couple weeks. I did find out after like a few months, it starts bonding to the tape and then you can't use them anymore. But if you store them for like a week like this, they're fine. It just protects them from dust and keeps the channels clean. This is what they look like aligned. And then before I learned about guide indicators, I was just putting a dot on the top mold because you have to punch the hole through the top mold so that you can access the bottom channel. So you can either do that by putting actual like indicators in your design, which I have in the design that's published. There's like little dots here, and then I put little dots here so that I know where to biopsy punch, but you can also just put them together and then draw the dots. So then you need to use like a biopsy punch, which is a little guy that cuts a circle. And I really don't like working with the tubing and the syringe pumps. It's very annoying and takes a lot of equipment, and it's very complicated getting into a cell culture hood, and then you got the syringe pump and you got all this tubing. I had a lot of issues with it. Controlling the pressure and the flow rate, I did not like it. So I'm lazy. I was like, you know what? I'm just going to put some pipette tips in the channels, and it worked. And then I found other people have done this too. I did a 1 mil pipette tip, and these are 200 mil filter tips with the bottom cut off to keep it sterile. And this was enough. I don't think I used antibiotic for this culture, and I still didn't ever get contamination. And as long as you change this daily or every other day, you can have like 1/2 mil of media in here. And then I put it on a rocker plate and tilt it this way and this way. And that makes sure that the media is getting exchanged enough. You do need flow in these devices because the cells do eat a lot, and they will not be happy. They'll get really hypoxic very quickly if you don't have flow of some kind. It doesn't have to be tubing, but it needs to be some kind of larger media reservoir that is being fed to the cells with something. And then I did a little bit of staining to show I got a nice confluent monolayer. This did not happen every single time. Some devices just fail, but the key is you want like a 75 to 90% success rate. And you can tell just visually if your cell culture worked with a bright field microscope. I didn't show that picture, but I have pictures. You can see the cobblestones of the cells. And that's why we like PDMS, because it's clear, you can see through it. These are the publications that go into more detail about the technology. I'm happy to answer any questions about it here and via email. And I really encourage you to check out the papers, because I think that I'm better at writing than talking, so you might get more out of them. But I hope that this was helpful, and yeah, I welcome any questions.
Thank you so much, Dr. Viola. That was a really nice presentation. We already have some questions in the chat, but others, if you have questions, then please feel free to type out your questions either in the chat or in the Q&A column. I'll start out by asking the couple of questions that we already have here. So one question is, does your tool ever break during milling? And what lubricant or cooling fluid do you use during milling, if any?
So Vishwa and I have broken, I don't want to call you out or anything, we've broken a number of tools, and that's because this is an empirical process and we don't always exactly know what's going to work for your protocol. And the tools are like a little bit expensive. It's like $100, $150. Is that about right, Vishwa, from your memory?
Well, the finer tools are more expensive. The bigger ones are cheaper, maybe 20, 30-ish. Yeah.
Yeah, but it's never the bigger ones that are breaking, right? It's the tiny
True.
ones.
Yeah.
Yeah.
Yeah, the tiny ones, yeah.
But, you know, they're a couple $100 max. I've never seen anything more than like, do you think that's about right? They can be higher than that?
Yeah. No, I don't think so.
What's the most you
Not
spent on?
Probably like 150. And I went down to one of the smallest tools they had available on the website. So yeah.
Yeah.
Doesn't
That's
go
main,
more than that.
like the main limitation is the size of tools that you can buy. And I think that's probably also to do with like what's physically possible with metal. I don't know how they make these tools, but I don't think you get much smaller than like 1 micron, right?
5, I think, is the smallest I've seen. Yeah.
Okay. I've seen people do 1 micron features. I don't know that there's a tool that small, but you can still mill outside of the features and get 1 micron. So yeah, it depends on your design. 5 microns is still really small though. And if your cut is not optimized, if you have too much on your chip load or you have an accidental collision, which can happen, you might lose a tool. We have a tool graveyard. It's okay. It's not like the tools are, you know, you don't want to break a tool, but it happens every once in a while. They're not insanely expensive. So it does happen, and that's part of the optimization process. And one of the reasons that you want a good optimized cutting plan so that you're not putting as much strain on your tool and you're not as likely to break the tool. But if your tool is breaking, it's an indicator you need to go back and optimize your simulation better so that your tool is Ideally you want to be, the first time you do a cut, if you have a microscope camera on the tool, you want to stay for a while and watch the cut happening so that you can see what's going on. And if there happens to be a break, you might be able to see why it happened. Maybe it was a collision, maybe you were just cutting and then it broke. That means maybe that particular cut needs to be optimized or more slow or a different set of spindle speeds or a different size. But there's so many variables, and it's just kind of trial and error when those things happen. And if your cut is going to be 14 hours long, you don't have time to sit there and do it. Sometimes some of the microscope cameras do record those, so you could record a video and come back and look at it. So yeah, I think that, and then the coolant, we used to use a lubricant provided to us by like the fabrication core. I stopped using it because it didn't really seem to do anything. Have you used a lubricant, Vishwa?
No, I think our devices are usually air lubricated, so we have a constant stream of air on the tool, and that removes any chips that prevents them from clogging around the tool. So it's technically air lubricated, but no separate coolant. At least I did not need one.
Yeah, the other reason I didn't like to use a liquid lubricant is because I don't want to get my device covered in lubricant. I don't know how to get that washed off, and these are really small channels. And I don't know if that would mess anything up with my casting later. So we just use an air nozzle. Most of these devices will come with an air lubricant system because you practically can't do this technique without it.
I would say that if you were machining metal, then maybe it heats up more. But since we are working with plastic, that doesn't heat up too much.
Yeah. And then while we're on the subject, one of the other concerns with your lubrication system is that your tool, our tools are so small that it's possible that pieces of whatever you're milling are going to get stuck in the tool. And we call that like clogging the flutes. So while you're cutting, you were cutting off pieces of plastic, that can create a lot of friction, which can create heat. And that's what the air is supposed to help with, is both getting rid of the chips before they can melt onto the tool and also cooling off the tool a little bit. But if you're seeing like high surface roughness, one of the causes could be that you're clogging your chips into the tool, which is like compromising the tool's ability to cut. That could be because there's too much heat. So you might want to take down your spindle speed, take down your feed rate, because you could be generating a lot of heat. Another way to tell that is to physically look at the tool while the cut is happening and see if the tool, you can sometimes pause in the middle of your protocol and look at the tool and see if it's full of plastic. So that's one downside of cutting plastics. They don't have a low melting temperature, but they do melt easier than something like metal. So it's something you got to be aware of. I have not heard of trochoidal milling. I would have to look into that. So this is the only milling technique that I've personally done. I've worked in a manufacturing center that did CNC machining on large scale parts like pipe fittings, but I didn't know about this. This is interesting. I'll have to look into it. Is acrylic the only substrate that we use? I've never personally done PMMA, but I know people do it and it should be fine. I mean, it might require different optimization. Every material is a little bit different. But I've read papers that mill PMMA. I think an example is in my protocol, actually. So it's definitely millable. And I know some people like to use it to directly fabricate the device rather than making a mold. I think I like to cast PDMS for my applications because it's clear and it tends to be really compatible with cell culture, but it depends on what you're doing. PDMS can absorb some chemicals and some proteins in a way that you might not want for like point of care applications or like chemical reactions. So you might want to directly mill your part if you're doing something like that.
While we're on that topic, we had a question sent to us before the seminar, and the person wanted to know if you could directly mill a specially treated PDMS so as to make it maybe more stiff. Have you heard of any techniques where they treat PDMS specially to make it millable?
I don't know that would work. Do you? I don't have the sense that would really work. Do you think so?
No, because I think if you make PDMS stiffer, it also becomes brittle, and then I think you don't want very brittle material. So I don't think that I've not heard of it in my limited experience. I don't think it will work. Yeah, but I could be wrong.
Yeah, I mean, me too. It's you're welcome to try it. If you got a micro mill, throw some PDMS on there and report back in the comments. We'd love to know, but I have a sense it would be pretty difficult because if your PDMS is very stiff, like you said, it's going to crack and it's not going to be really good for any, like you might not even be able to plasma oxidize it if you don't have any free moieties. And if it's flexible and it's not overly cross-linked, it's too flexible and you're not really going to get clean cuts. You're probably going to get some breakage of the PDMS. So you want a stiff material that's relatively brittle, that's not kind of more fluid. You need it to be a stiff material that will hold its shape that you can cut into. So like metal, wood, plastic are the ones we always mention. But, you know, because the tools are relatively inexpensive and accessible, I would say throw whatever material you want on there if you're willing to break a tooltip. And you can just see what works. Does the machine cool tool by time at night? I think the machine stays cool pretty well. I don't know that I necessarily understand exactly the question, but I think the machine can stay cool as long as your cutting plan is reasonable. If you're overheating, you're just going to have a bad cut, but it's not going to hurt the machine. But you'll know if it was bad, you're going to come back and be very sad in the morning. So could micromilling be applied in the fabrication of biomedical devices for drug delivery? Can the substrate be modified so that micromilling works while being more flexible for practical applications? I think it definitely can be used. The advantage of micromilling is that you can kind of cast other materials onto it. You could cast alginate or PDMS or whatever other hydrogel if you're making a hydrogel-based device. You can also, you know, mill PDMS. You can't mill. We just covered that. You can mill PMMA, which I think is implantable. If you had a high molecular weight PLG, you might be able to mill that, or PCL. I think those would probably be millable because they're pretty solid at room temperature. But it would still be kind of an experiment. And then could substrate be modified? Yeah, I mean, I don't know. I think it really depends on your application. I'm sure you could try different polymers and just try it and see what you get. This is a relatively underutilized technique in biomedical field, I think. So I don't know that we have the answer to these questions. I'm excited to see what people do with it. I hope people use this technique more, and then we'll maybe figure some of that out. But I don't exactly know what materials we can use. I would say the most guaranteed thing to do is make a mold out of acrylic or something and then cast other materials onto it. If you have a photo cross-linkable polymer or a heat cross-linkable polymer, you can just pour it onto the mold and then cast it. That's your most likely to be successful, and you have a higher throughput because you can make the mold and then do lots of devices from that mold.
Would you like me to read that aloud? Okay.
For microfluidic channels that contain small radii on the longitudinal axis, do you utilize a bullnose and mill with small step down, or do you select a specific tool that matches the solid model's radius feature? So I do the first one. I take a bullnose with a small step down. In my simulation, you'll see that I actually went, hold on, I want to go to that slide. I actually didn't go longitudinally across. I did like do the, I don't know why it just did this. Sorry. I wanted to show the exact slide. So the way that I ended up doing it for my channel was to take, let me reshare. All right, are we back? So I took like a smaller tool than my diameter. The first cut that I did, I went all the way across the channel with a bigger tool just to clear the material. But for the final surface finish, most of it I ended up doing kind of this way with a smaller tool going back and forth. And the reason for that was I did not want to get ridges. See this kind of longitudinal ridge? That's because I used a bigger tool and I wasn't trying to go all the way in. but I found this gave me kind of a smoother surface finish with less artifacts when I did it like this. But if your channel is so small that you can't do this because the smallest tool is like 5 microns, then, you know, other things might work for you. What would be the resolution in the Z direction? How would it depend on machine and what machines you recommend? I think the resolution is probably more limited by your tooltip size than by the machine itself, because like any micro mill, they're going to have different XYZ resolutions, but they're around like 0.1 microns most of the time, I think. At least ours is. I think the machine cost depends more on how fast your spindle speed can go than the resolution. Do you know anything about that, Vishwa?
I do not, but I do seem to recall that our machine is on the like the better edge of the spectrum, where we have a better resolution in Z-axis compared to some of the other models. I don't remember off the top of my head what other mod machines have, but ours does go to 0.1 micron, so it's a fraction of a micron, which is pretty small, and it's one of the better ones out there.
Yeah, and it was still, I think ours was 10 to 15K. I wanted to include that because if anyone's, you know, going to invest in this technique as an institution or an individual, you know, having a ballpark of like, is it like $1 million or $10,000 is useful, but it really varies a lot by the tier of machine that you get and what spindle you get, because they're sold separately, the machine itself and then like the spindle and everything, you know, they sell it part by part. But I think for most applications, you're going to be more limited by the tooltips available than necessarily by the resolution. The Z-axis resolution is going to be the same as XY. It's still 0.1 microns for our machine. So the channel that I made was much larger than that, and most microfluidic channels are going to be on the micron scale. So the resolution will be good enough that you're not getting these ridges. Like there was a very slight, I think the surface finish in the simulation is very faithful to what my part ended up actually looking like. So you can tell that it was milled, but it's not so disruptive that it was going to affect my part, or, you know, that it was no longer, like it was still optically clear and everything. And that's good enough for me. So could this be used to build a 3D platform for studying endometrium? Absolutely. I think it'd be great for that. I think I included the sandwich device design in the protocol because that's a really common one. I don't know if your design would need 2 layers, but a lot of the time we want to have a top layer and a bottom layer because we're trying to study some kind of barrier where there's endothelial, epithelial. That structure is really common in the human body. And in order to do that, you need 2 channels on either side, and then you have to have some separating membrane in the middle. And the technique that I used that's included in my protocol will allow you to get a nice well-sealed membrane that does not leak when you do cell culture, because that's the other thing. It might not leak when you make it, and then you put it in the incubator for 2 weeks under like 95% humidity, and it's full of liquid. And that's when you start to see the leaking problems. So I really like this protocol. It worked for me. I didn't have any problems with leaking. And I tried other stuff. I tried the stamping method where you kind of stamp the top channel onto liquid PDMS. It really didn't work. I mean, this design in particular, you could really just take out the T from the channel and just use the straight channel. And it would work for most things. The only reason I have the T is that in my paper, I included an air inlet and a liquid inlet. And you could also make this flat. It's only 3D because of what my particular application was. But it's also important to like consider, do I actually need the channel to be round? Because the micromill doesn't have to do 3D. It can, but it can also do the normal 2D stuff and still be cheaper and easier to do prototyping on than photolithography. And a lot of times flat is better because the roundness does make microscopy annoying. It kind of distorts a little bit. So my images, I think I took them on an inverted fluorescence microscope through the filter, but you can also take off the filter and mount it and stain on a slide if you really want really good imaging. But that's what you have to consider. A major endpoint of organ on a chip is going to be imaging. because it's super hard to get enough volume and enough cells and any biomaterial to like really do PCR sequencing, flow, ELISA, like all the stuff you'd normally do is pretty difficult. It's not impossible, but it's harder, which means imaging is a lot of times a common outcome. And if you're doing 3D features, you have to consider that. How are the molds aligned? In what I ended up publishing, I added the alignment indicators here. So I put on the top and bottom, I put just a little button. But when I did it when I actually made them in grad school, it didn't occur to me that I could do this. So I just did it by hand in approximately the same spot every time. But I recommend putting some kind of indicator. People will do like a plus sign sometimes, or you'll see like a plus sign in each corner. Some people have devices so small that you need to align them with like a microscope. You get on a stereo microscope and you can see the plus signs and align them. I didn't find that necessary for me, but mostly I would just recommend some kind of alignment indicator on the top channel and the bottom channel in your design. Any other? So I think we talked about the spatial resolution. So point of care devices and drug delivery. These are the other two questions that we got in the pre-chat. I think we definitely can fabricate biomedical devices. It really is, the sky is the limit. There's a lot you can do. Can we use this for patients? What are the major ethical and regulatory issues? I don't know. I know that it really is going to depend on your institution, your country. I've collected patient specimens before with clinicians, and usually the clinicians, if they're doing clinical studies, they will have their own institutional permission set up, and you might just be able to join their paperwork thing. There in the US, it's called an IRB. You might be able to become part of their IRB and then get your lab added as a location for their IRB, and then you don't have to make your own because it's a whole process. That's what I would recommend for getting tissues. If you can put human specimens in these devices, I would work with clinicians or someone already collecting specimens, because making your own plan takes a while. It takes a long time to get approval and everything. You can definitely put microfluidics on a microscope. I had a custom setup where I did that. And again, it's just a consideration of the shape of your channel, how thick your device is going to be. You might want to specifically design it as a certain size and a specific volume of PDMS so that it's the same thickness every time. And thinner is better for microscopy. I think you can get some pretty good images, though. People more advanced than me have done really impressive imaging on microfluidics. And just one more advantage of micromilling: if it doesn't work, do a new design. You'll have it the next day.
Thank you. Thank you so much. I think that's all the questions we have in the chat right now, and we're way over time, but thank you so much for sticking around and answering all the questions.
Thank you so much, everyone, for attending and for an amazing talk and great moderation. And yeah, thanks. This was great.